Okay, 3:35, I think we can get started here. Welcome everyone to the Wulff Lecture, the DMSC Wulff Lecture. I'll just say a couple words and then introduce our speaker. This lecture is called the Wulff Lecture, and that's because it's named after Professor John Wulff, who was a professor in the Department of Material Science and Engineering. And he was also an outstanding teacher, an educator, and lecturer. And in fact, he was the originator of the class 3091. Anyone here from 3091? Yeah. All right, all right. And if you look at photos, and I don't have one here, but I'd show it if I did, of John Wulff lecturing, he was animated. And he was really an exciting lecturer and deliverer of our discipline, right? What do? We build matter out of atoms. We understand how atoms interact. We understand how they come together and make solids, and we understand what we can do with those solids. And one of the most and so we created this lectureship that's named after him as a way to kind of each semester have a topic and a person who's really an expert and world expert and leader in that topic to come and inspire our students, just like John Wulff did. And you know, it just so happens that one of the most interesting materials that's no offense to metals and semiconductors, but glass is such an interesting material. Actually, you can make metallic glasses, but that's a different use. But anyway, we shouldn't get into it. But glass is so interesting, and it's taught in 3091. And it just so happens, I believe, that today you broke glass in 3091. Is that right? Yeah, that's pretty cool. And so I'm just so excited that this is also the day when we have one of the world's most leading experts and innovators in glass as our Wulff lecturer. It also happens to be the year of glass, and that is Professor John Mauro. And he's the Dorothy Pate Enright Professor and Associate Head for Graduate Education in the Department of Material Science and Engineering at Penn State. He got his degrees in glass science, glass engineering science, and computer science at Alfred University, and then he joined Corning. And he was there for 18 years, and he's a co-inventor and inventor of many things there, but one of the things he co-invented is Gorilla Glass, which is made quite a change in the world, just that one material itself. He joined Penn State in 2017, world recognized expert in fundamentals and applications of glass. He's a fellow of the National Academy of Inventors. He's got over 69 patents, 20 pending. He's also a fellow of the American Ceramic Society, the Society of Glass Technology, and a member of the National Academy of Engineering. So I am just super excited to welcome Professor John Mauro to our Wulff Lecture today.
Thank you so much for your kind introduction. Thank you for inviting me here for the Wulff Lecture, and thank you all for turning out both in person and online for those of you who are joining us. My name is John Mauro from Penn State University, and I'm here to share with you my love of glass and more broadly my love of material science and engineering. This is a field that has a little bit of everything. If you're interested in chemistry, it's got chemistry. It's got physics. It's got engineering. If you like theory and modeling, you can do it that way. If you like to make things, you can synthesize materials, characterize them. You can use them in brand new applications to help address global challenges related to energy, the environment, and so on. It's an amazing interdisciplinary field. I love it, and I want to share some of that love for you. So the title of my talk today is Perspectives on the United Nations International Year of Glass. And I would like to start with this article which appeared in the Atlantic Monthly magazine called Humankind's Most Important Material. Glass has changed the world unlike any other substance. Now, of course, all types of materials have brought us to where we are today, whether it's metals or ceramics, polymers, composites, and glasses are, of course, a key part of that and a key enabler for modern civilization. Now, when we think about glass, some people think of it as being an old-fashioned material. And indeed, it's been around for thousands of years. And many of the common glass products that we look at, it's not something that we really look at, but it's something that we look through. We look through our windows. And so let's take a moment and really pay attention not to what's on the other side of the glass, but to the glass itself. So common everyday things that we take for granted, like the ability to bring in this beautiful natural lighting on this sunny Cambridge day into our lecture hall, without having to worry about the harsh elements outside. Eyeglasses. So could you imagine, so I've had these since I was, 12 years old. Could you imagine going through life not being able to see clearly once your vision degrades? Glass has been key not just in itself, but it has enabled entirely new fields of study. So glass lenses and the invention of telescopes were key to take astronomy from something we just did with the naked eye to bringing it to where it is today with the James Webb Telescope. So all of these astounding images that are being brought to you today are made possible by highly engineered glass products. If we go from the large scale down to the micro scale, glass lenses and microscopes were key for discovering the entire world of subatomic or single cellular organisms and the fact that diseases were caused by these organisms. So the whole field of microbiology was really made possible by the use of glass. Having just gone through a pandemic, we know that glass is key as a storage material, not just for everyday foods, but also for medicines that are needed to cure diseases and for vaccines. And it's really important to have a material that is going to store those medicines safely through its mechanical strength, as well as not interact with those medicines to change how it behaves. And so glasses have been a key part in our response to the COVID-19 pandemic. The entire world is connected by really thin strands of glass. So optical fiber, invented at Corning back in 1970, are approximately 125 micron thick strands of ultra-high purity silica glass with extremely low optical attenuation. Our entire world is connected by fibers now across continents, under oceans. This is what made the internet possible. This is what brought us into the information age. And behind the scenes there, it's all glass. Glass is essential not just for communicating information at the speed of light, but also for displaying that information, whether it was the old-style cathode ray tube displays or modern flat panel displays, or the displays that you carry around in your cell phone. All of that is glass technology. Every one of these displays has at least 2 highly engineered thin sheets of glass in there with specialized thermal properties, chemical properties, optical properties to make this happen. I spent many years of my career working on exactly that. And speaking of smartphones, there's also this computer that you carry around in your pocket that has at least 3 pieces of glass, 2 for the display, and 1 which is the Gorilla Glass cover. This is what makes it scratch resistant, impact resistant, drop resistant. Again, it's all highly engineered glass technologies. And finally, transportation. That's not a picture of my car, but it's a very nice car that has, of course, glass windshields, and some cars have fiberglass components too, to enable high strength and low weight. So because of this tremendous importance of bringing modern civilization to where it is today, we actually petitioned the United Nations to declare this year the International Year of Glass. This was an idea that started back in 2006 with my former dean, David Pye from Alfred University. He actually came to me with this idea, and at first, honestly, I thought, no way, this couldn't be done. But led by David, we put together this international team and made it happen. So this was actually approved by the UN General Assembly. So 2022 is the official UN International Year of Glass. It's the first time any material has been given that honor, and I expect there'll be more to come in the future. So the International Year of Glass is not just looking backward at how glass brought us to where we are today. It's also looking forward to see the new opportunities that glasses can offer. So In this vein of trying to figure out the biggest impact that glass has had, my advisor Arun Varshney and I, when we were putting together our glass textbook, actually sent out a survey to 91 experts in the field to ask them to rank the top 10 glass products or processes that have had the greatest impact on humankind. And you can see the results ranked there, a very long list. Colored in blue are glass products, and colored in red are glass manufacturing processes. This is something that sometimes we overlook as material scientists. It's not just about the material itself, but also the ability to make it, and to make it with consistent quality, at low enough cost, and at large enough scale. And so these process innovations are just as important as the product innovations. But what you see here are that optical properties are extremely important. Sometimes they're the most important properties, like for glass lenses and optical fibers. Other times we just need something to be, basically transparent. Mechanical strength is a key property as well to make sure that these glasses can be used without breaking. It's still a challenge that we're still making progress with. Chemical durability of glasses, too. This is why we can have glass windows that have survived for centuries without dissolving in the rain because of their high corrosion resistance. And the other thing we note is that even though in principle you can make glasses from any liquid that can be quenched fast enough, thus far silicate glasses have been dominant in terms of their impact on humankind. Now, as materials scientists and engineers, we tend to think of materials in terms of their physical properties and their engineering applications, but it's also important to understand and consider some of the cultural aspects of materials, because everything is made out of materials. It's not just our engineering widgets, it's great works of art. It's so integral to our culture. And the beauty of glass has captivated humankind for thousands of years. If you go back to my hometown, to the Corning Museum of Glass, you'll see the history of glass there and all the beautiful art that has been made there. That's what captivated me as a young child when my parents took me to the Corning Museum of Glass when I was just 6 years old. And I loved all the little glass animals that they made and all the different colors and shapes that they could have. I wanted to see every single piece of glass in the museum. I also loved computer science as a child. I loved programming, and I had my own software company in high school and college. And I wanted to put those two passions together. And everything clicked for me when I saw this great video from Professor Alexis Clare at Alfred University. It was like a Bill Nye the Science Guy type video where she'd pop up and do all kinds of goofy things. But she basically was talking about all the different applications of ceramics and glasses. And the thing that captivated me the most was this idea of optical computing, of using glass components and propagating light and doing computations at the speed of light. It's like everything came together for me. So I went to Alfred University. I did a double degree in computer science and in glass engineering science. And by the way, double degrees are great things for those of you who are still figuring out what you want to do. It gives you a real competitive advantage out there when you can combine two things like that. And computer science is a great field, a powerful field, but when you couple that to something else like materials, you can take the next step beyond. So from there, I went to Corning Incorporated. I spent 18 years at Corning. For the first 11 years, I was in the modeling and simulation department, doing more sort of theory and modeling and software-related stuff. And then I spent 7 years in the glass research department doing more experimental work and new product development. I had a chance to work with all kinds of wonderful people on great products, including the Gorilla Glass product on your smartphone. So one of the things that we noticed at Corning was that it was becoming increasingly difficult to find well-qualified people to hire. We had openings. We were looking to try to hire experts in glass. And many of the professors that we had relied upon were retiring and not being replaced. And it was becoming a serious problem that we just did not have the stream of students coming in who were trained in these areas. So we did a study to analyze the number of papers that were being published as a function of time. and as a function of country in glass science. And what we saw is that in the United States, the US was on top for most of this history, but it kind of peaked in the mid-1990s and even started to decline a little bit. Similar type of story in Japan, which had an even larger drop, and in some of the Western European countries. Meanwhile, in China, there was zero glass research going back to the 1960s, and they have grown exponentially. And at this point, when we did the study, we're doubling the output of the United States, which this taught us two things. One is, of course, we need to engage more with all the wonderful research that's being done in China, but also we need to do more to promote glass research in the United States. So we put together our Corning Glass Summit to try to convince more people to work in glass. But we also basically wanted to convince universities to hire more professors in glass. So my boss told me I took the problem a little bit too seriously when I quit my job to go do exactly that. I went to Penn State in 2017. Here I am with my family. This is my wife, Yihang, and our daughter, Sophia. So we joined the Penn State Department of Materials Science and Engineering back in 2017. This is one of the more recent pictures of my group there. And it has been just a pleasure and an honor to work with so many great colleagues there, and most of all, with the wonderful students who are coming in with so much passion for learning and applying that knowledge towards making the world a better place. So back to glass. Where does this word come from anyway, glass? So the word glass comes from the late Latin term glacium, and that is used to refer to a lustrous or transparent material. So this idea of kind of the transparency and the beauty of glass it's built into the word itself. There are a couple of other words that are sometimes used to describe glassy materials. One of those is vitreous. Vitreous and glassy mean the same thing. Vitreous also has a Latin origin. It's from vitrum, which also means transparent or clear. And another word is amorphous, coming from the Greek amorph, meaning without form or shape. Now we have to be careful here because amorphous materials are actually a distinct class of materials from glasses. They're both examples of non-crystalline materials, but there is a key difference that I'll get to in a little bit. But glass, the history of glass goes back to about 12,000 BC in ancient Egypt, where glass beads were found there. And glass has been a key part of humanity ever since then. Now, the oldest recorded glass making is from about 3,300 years ago in ancient Mesopotamia, in what's modern-day Iraq. This is like the original lab notebook for how to make a glass. And it's actually kind of amusing how they did this. Let me read this. When you first set up the foundation of the kiln to make glass, you must first search in a favorable month for a propitious day, and only then you set up the foundation of the kiln. As soon as you have completely finished in the building of the kiln, and you go to place the kubu images there, no outsider or stranger should enter the building thereafter. An unclean person must not even pass in front of the images. You regularly perform libation offerings before the kubu images. On the day when you plan to place the glass in the kiln, you make a sheep sacrifice. Before the kubu images, you place juniper incense on the censer, you pour out a libation of honey and liquid butter, and then only you make the fire in the hearth of the kiln and place the glass in the kiln. So if you see my students at Penn State making sheep sacrifices, you know they're about to melt glasses. But this is amusing, but it gets to the point that glass making is sensitive. So it depends on the choice of your raw materials, the purity of those raw materials, choosing the right things. They didn't have X-ray diffraction back then. They didn't know quite what they were putting into this. What they would see is sometimes it seemed to work, and sometimes it didn't work. And it was kind of random about when it worked and when it didn't. So, of course, that was all attributed to the superstitions of the time. The glass has really been ahead of its day. So, zooming ahead now to the 4th century AD, this is the Lycurgus cup, which is 4th century Roman glass. And what's really interesting about this is that it's dichroic. It has two different colors depending upon the lighting conditions. So in reflected light, shown here in green, there are metallic nanoparticles in this Lycurgus cup that are just coarse enough to reflect some of the light without eliminating transmission, giving it a green appearance. In transmitted light, the fine particles scatter the blue end of the spectrum more effectively, giving a red light. So this is actually nanotechnology from the 4th century AD. There are little nanoparticles of gold and silver in this Lycurgus cup. And today, people still have not been able to reproduce this exact effect. So way ahead of its time. But what is glass? I think we have an intuitive feel for what it is because we've seen so much of it. But what is it really? And to understand what glass is, we need to understand the concept of equilibrium. So some of you this morning might have had a cup of coffee to start the day, and maybe with some cream in that coffee. So if you have a mixture of coffee and cream, I ask you, what is the equilibrium? You pour the cream in, you get a homogeneous mixture of coffee and cream. Okay? Then if you don't drink it, if you just let it sit there, it's going to reach, the coffee and cream mixture is going to reach a temperature equilibrium with the room it's in. It starts off hotter than the room, and it's going to end up at the same temperature as its environment if you wait long enough. Okay? And if you wait even longer, there's going to be some evaporation, and you're going to have a vapor equilibrium. So, which one of these is equilibrium? How many people think this first one is the equilibrium? Anybody? Chris, okay, good, good. How many people think this second one, the temperature equilibrium? Yeah, that's gotta be it. Okay, good. How about this third one, vapor equilibrium? You waited really long, so that must be it, right? Okay. So what is it? Let's ask Richard Feynman. So one of Richard Feynman's many great quotes is that equilibrium is, quote, when all the fast things have happened, but the slow things are not. I know what you're thinking. Surely you're joking, Mr. Feynman. But there's actually a really great insight here that, what is fast, what is slow? And it's really up to you as the individual observer or the experimenter, or how you are experiencing the system to choose the relevant time scale. If your relevant time scale is that you want to drink this coffee in a few minutes, the relevant equilibrium is the coffee-cream mixture at shorter times. If you are, a fan of Fourier and you want to study, temperature equilibrium, then it's the middle one. Or if you want to study vapor equilibrium, it's the third. So it's up to us as the experimenters, whether you're doing a simulation on different timescales or your experiment on different timescales, to choose the relevant timescale on which your processes are occurring. So why do I bring this up? What is glass? This is the definition of glass. I'm going to read the definition, and it's going to sound weird, and then I'm going to explain it, and then it's all going to make sense. So glass. Glass is a non-equilibrium, non-crystalline state of matter that appears solid on a short time scale but continuously relaxes towards the liquid state. Whatever do you mean, Dr. Mauro? Let's explain with this diagram here. This is the volume temperature diagram. And what we see here is if we start at high temperatures and high volumes, let's start in the liquid state here at point A. This is a nice, happy equilibrium liquid. The liquid, of course, has a non-crystalline structure, but it's in thermodynamic equilibrium at this particular temperature. Now, what happens as you cool the liquid? If you cool the liquid to just below its liquidus temperature, what will happen in equilibrium? It will undergo a first-order thermodynamic phase change with a discontinuous change in all of our favorite thermodynamic properties, the volume, the enthalpy, the entropy, and it crystallizes. And so the new equilibrium at lower temperatures is the crystal. And if you continue to cool the crystal will contract according to its thermal expansion coefficient. So crystallization, is it something that happens instantaneously? No, it takes time. It takes time for the atoms in the disordered non-crystalline structure of the liquid to reorder themselves into a crystalline configuration. In some liquids, this happens very quickly, like water, for example. If you take liquid water and cool it below 0 degrees Celsius, it crystallizes quite readily because it's so fluid at that temperature. But if you take something like silica, if you cool silica below its freezing point of like 1727 degrees Celsius, it's incredibly viscous. It's thicker than honey there. And it's really difficult for it to crystallize. And so what we have here is a combination of thermodynamics, Is there a thermodynamic driving force to crystallize? And then kinetics. Can it actually happen? And the reason that we observe glasses is because of the latter part, because of the kinetics. So if you take a liquid that's difficult to crystallize and you cool it fast enough through this regime where it's likely to crystallize, you cool it so fast, the atoms simply don't have time to keep up. Then you get what is called a supercooled liquid. A supercooled liquid is just any liquid that's cooled below its normal freezing point. From a thermodynamic point of view, this is not the stable equilibrium. The stable equilibrium is the crystal. It's what's called a metastable equilibrium, meaning it's stable on its own if it's unperturbed, but giving it a large enough perturbation, it can undergo a first-order thermodynamic phase transition and find a state with a lower Gibbs free energy, namely the crystal. Now, if you take this supercooled liquid and continue to cool it, as you're cooling the system, you're extracting more and more thermal energy, and the atoms are no longer vibrating so fast, they're kind of slowing down and getting really sluggish as they gradually get frozen in. Eventually, the time scale of this atomic motion becomes slow compared to your observation time scale. And when that happens, this metastable supercooled liquid, that structure is gradually freezing in. It's going through what's called this glass transformation range or glass transition range, freezing in so these configurational transitions of the atoms are no longer possible on your time scale of observation. You get a material that has the frozen-in structure of a liquid that, for many practical reasons, behaves just like a solid. If you drop it, it might break. But its structure is that of a liquid. And this material is what we know and love as a glass. So it combines some of the properties of solids with some of the properties of liquids. But it's also its own thing because of being out of equilibrium. So if the crystal is equilibrium, the supercooled liquid is metastable equilibrium. The glass is an unstable state. It is a non-equilibrium material. And if you hold it for long enough, it is going to be constantly relaxing, constantly trying to approach the supercooled liquid state. But this happens over very long time scales. And so when you consider now this definition of glass once again, it's a non-equilibrium material. What does that mean? It's not the thermodynamic equilibrium. It also means that the state of the glass depends not just on its chemistry and its temperature and pressure, but its entire thermal history and temperature history. Here you see if you cooled the supercooled liquid fast, it freezes in the glass at a higher temperature because you've given it less time. And therefore, the structure of this fast-cooled glass corresponds to the structure of the supercooled liquid at a higher temperature. This temperature, by the way, is what we call the fictive temperature, TF. Fictive literally meaning fictional. If you take a liquid and you cool it more slowly, it's able to stay in the metastable equilibrium longer, falling out of equilibrium at a lower fictive temperature, and therefore the structure of this more slowly cooled glass, it more closely represents that of the supercooled liquid at the lower fictive temperature. So this fictive temperature is an additional thermodynamic parameter. You need to know the chemistry, the pressure, the temperature, and something else to tell you the non-equilibrium state of the glass. The simplest of those is this so-called fictive temperature. So the glass transition here, this transition between the liquid and the glassy state is key to understanding what glass is. It comes from the liquid. It will return to the liquid if you heat it back up. The structure of a glass is very similar to the structure of the liquid. They're continuously connected together. This is what distinguishes glass from amorphous solids. Amorphous solids do not have a structure similar to the liquid, and if you heat them up, they do not undergo this continuous transformation to a liquid. They will crystallize. And so this glass transition, it's actually a fascinating problem. Even though glass is one of the oldest materials, it's also one of the least understood. And one of those aspects is this glass transition, this connection between the liquid and glassy states. And in fact, Nobel Prize winner Phil Anderson is once quoted as saying that the deepest and most interesting unsolved problem in solid state theory is probably the theory of the nature of glass and the glass transition. And so this is an area with a lot of devoted research and still a lot that needs to be done. Now, what about us as somebody who wants to design a glass to address next generation challenges? One of the interesting things about glass is because of its non-crystallinity, it doesn't have to obey the same rules of stoichiometry as crystalline materials because you don't have this periodic lattice anymore. And because of that, you've got nearly the entire periodic table at your disposal in terms of things that you could potentially put into a glass. And the composition itself is infinitely adjustable. So there's basically a continuity of different glasses that are possible. And when you change the chemistry of the glass, all the properties are changing. And so the question becomes, how do we design the right one? How do we get the right chemistry to give us the right combination of properties? Now, anytime we're designing a new glass or any type of new material, there's always like two sets of properties that we care about. On the left-hand side here, what I'm showing are kind of product-related attributes or end-user attributes. These are properties that affect the performance of the product. So if you take Gorilla Glass, for example, its damage resistance, its chemical durability, its hardness. These are all properties that we care about as end users. But then there's another set of properties that need to be addressed in order to make this really change the world. Because it's not enough to just make a single piece of Gorilla Glass in my lab and like I'm the only person who can use it. That's not very kind of me, is it? We need to make something that is going to be manufacturable at large scales so that everyone can use it and that it can be affordable and have consistently high quality. So there's another whole set of properties that we care about from a manufacturing point of view. So when designing the new materials, we have to pay attention to both. If we want to change the world, we have to do it with both. Modeling is a key part of this. So obviously, we've got lots of experimental data that we need to use. But modeling is just as important as the experimental data to understand additional details about the glass structure, to try out different glass chemistries, and to sort of build the most holistic view of glass. It requires both theoretical aspects as well as experiments. When I say modeling, it's not just one type of modeling. It's like the whole toolbox full of different models. Everything from purely empirical models, like machine learning that uses large databases of data to try to discover relationships between glass chemistries and properties, all the way through very detailed models that account for the fundamental physics of glass, quantum mechanical simulations like DFT, and everything in between. It's all useful. It's all on the table. And if you're in a position where you need to solve a given problem, it's really helpful to have this big toolbox available so you can pick the combination of tools that will best address the problem. And when we have these models set up, if we have an accurate model for every one of these properties that we care about, all of the product-related properties, all of the process-related properties, each one of them as a function of composition, then the design of a new glass becomes really a mathematical optimization exercise where you've got some property that is like the most important property that you need to maximize or minimize, another set of properties that need to be met in order to ensure manufacturability. And if you do that, then you can get the next generation product. And that's exactly what this is. This is one of our Gorilla Glasses that was designed in exactly this fashion, with the old glass here underneath a 0.5 Newton scratch load, and it's getting some nasty lateral cracks that not only look bad and feel bad, but also greatly compromise the strength of the device if you were to drop it, versus the new glass, which is under a 50% higher load under the same type of scratching and only responds in a microductal fashion. So what's next? Looking forward, we know that glass has brought us to this information age, but there's more to come. If you see at some of the new phones that are coming out, for example, from Samsung, with foldable displays, flexible displays, these are being made possible by ultra-thin glass, 100 microns or less. We think of glass as being a rigid material, but if you lower the thickness down to under 100 microns, it becomes flexible. The thinner you make it, the more flexible it becomes. And so these companies are starting to build displays based on this ultra-thin, flexible glass. High refractive index glasses are also being used for augmented reality applications to superimpose images onto your reality. So if I were wearing these, I could see maybe all of your names floating above your head, or I could catch that Pokemon that's in the corner there through high index glasses that can refract the light with a small enough device. Quantum communication. So we need newer, even lower loss glasses for optical fibers to enable ultra-secure communication of quantumly entangled photons. Glass is also a medium for memory storage. Data can be stored in glasses three-dimensionally rather than two-dimensionally in glasses. And that data storage can last orders of magnitude longer time scale compared to, say, traditional magnetic memory storage. When it comes to transportation, the windshields in your cars, that technology has not changed much since the 1960s. But there are new glasses coming out now that will offer even better strength and performance of windshields and automotive glazing at a fraction of the thickness. And that will lightweight the vehicles, which reduces the fuel consumption. So it improves safety at the same time as reducing fuel consumption. Another big trend is in self-driving cars, autonomous vehicles. And if you're not actively driving the car, there's going to be more and larger infotainment systems, entertainment systems in your car. So while the car is driving itself, you can look at these pretty pictures of gorillas. For buildings too, so the standard now is double pane glasses with a noble gas in between. The next generation windows are what's called vacuum insulated glazing, where instead of having a noble gas, you pull a vacuum in between the two panes of glass to eliminate that mode of thermal transport. If you pull a vacuum, though, that creates stresses on these panes of glass. So these glasses have to be able to withstand that stress over many decades without fracturing. Glasses are used in all types of modern designs as well. They're helping to enable the Internet of Things and having more displays on appliances, greater internet connectivity. And for energy, glasses are key to renewable energy. So companies like Owens Corning that make fiberglass for these large windmill turbines. The larger the windmill turbines, the more efficient the wind energy generation is. But in order to produce larger scale windmill turbines, we need fiberglass with increased Young's modulus, so increased stiffness. So there's a lot of composition research going on now to try to take wind energy generation to the next level. Solar energy as well. There's several options there, including glass tubes that store algae to serve as photobioreactors, converting sunlight into chemical energy via photosynthesis. Glass that is used as a substrate for photovoltaics that is used on roof applications, as well as these that look like just ordinary shingle roofs from Tesla. Glass parabolic mirrors and glass tubing that is used for solar thermal energy generation to focus the light and convert it into thermal energy, which gets converted to electricity. And not just energy generation, but also energy storage. So Nobel Prize winner John Goodenough here, inventor of the lithium-ion battery, he is still actively doing research at, 100-ish years old, including the development of new glasses that should hopefully enable the next generation of batteries with higher density storage, greater safety features, greater cyclability. That's amazing. Healthcare, too. So I already mentioned about glass vessels holding medicines like, for example, EpiPens if you've got bee allergies, or the COVID-19 vaccine. There are new antimicrobial glasses that actually have silver ion exchanged into the surface to help enable antiviral, antibacterial, antifungal performance. So if there are surfaces that are touched by multiple people, like ATM screens or like screens in hospitals, this will help prevent the spread of infection. Because if you go to the hospital, hopefully you want to get healed and not catch some other infection that just happens to be there. And another really exciting area is bioactive glasses. Originally, these were for hard tissue repair, things like bones and teeth. But more recently, glasses have been invented for soft tissue repair, including this work by Steve Young and Delbert Day from Missouri, University of Science and Technology. They've developed glass tissues that can heal like ulcers. So like diabetic patients that have deep ulcers in their skin that sometimes go down to the bone and simply don't heal. When they're packed with these bioactive glass fibers, the fibrous microstructure stimulates the body's natural healing process. The glass degrades over time, giving the chemicals that the body needs to repair itself. And it's amazing that these patients who have had unhealed ulcers for years are being healed with these glass fibers. So what are we doing at Penn State? So this is me. I focus on glass composition research, bulk properties, theory, and modeling. My partner in crime at Penn State is Dr. Song Kim from chemical engineering. He's a surface scientist, and so he does everything related to glass surface structure, interactions with water, tribology, or wear behavior. And so maybe between the two of us, we've got a complete scientist. I've got in my group 2 assistant research professors, Young Jen, who does large-scale MD simulations, and Maziar Montazarian, who is an expert in glass ceramics and bioactive glasses. My postdoc, Hong Yen Kim, who does MD simulations of glasses. A visiting scholar, Eric Almeida, who works on crystallization of glasses. A lot of great PhD students they all have a passion for glass, but covering a lot of different areas of glass. Aaron Bosson is working on modeling of glass relaxation. Nick Clark is working on phase separation in glasses. Aubrey Fry on damage resistance in glasses. Katie Gerace on piezoelectric glass ceramics. Brittany Hockey on glass relaxation from an experimental perspective. Caitlin Kirchner on statistical mechanics of glass. Ye Luo on transparent glass ceramics, Adam on infrared transmitting glasses, Matt on phosphate and borosilicate glasses, Jessica on bioactive glasses, Shaylee on low melting temperature glasses, Rebecca on MD simulations of glass, and Don Shi on glass modeling and characterization. So every day, this is what I love about my job, is coming in and teaching my courses to students and working with this great group. So in this very last part of the presentation, I want to give you just one example of some of our recent research. And this addresses the issue of the carbon footprint of the glass industry. I've told you many great things about glass, but there is a downside, and that is that the glass industry, the global glass industry, produces something like 86 million tons of carbon dioxide each year. This comes from 2 primary sources. About 70 to 80% of that is due to the high energies that are required for melting glasses. Although I focused on kind of high-tech glasses, the fact is that about 95% of glasses being made and sold are the traditional soda-lime silicate glasses that are found in your windows, the glasses that you drink out of, and so on. So most of this comes from energy consumption, but about 20 to 30% of this comes from the decomposition of carbonate batch materials. So we call it soda-lime silicate glass because 2 of the raw materials are soda ash, which is sodium carbonate, that decomposes into sodium oxide and releases carbon dioxide, and limestone, which is calcium carbonate, which also releases carbon dioxide during the melting process. Another problem with high melting temperatures is that this molten glass is stored, when it's being melted, it's in a giant melter, like about the size of this room. If you imagine the walls of this room as being ceramic refractory materials like zirconia or AZS, and then this is full of molten glass at 1450 degrees C. Now, that's a harsh chemical environment, and that molten glass degrades the walls of the melting tank over time. And the higher the temperatures, the faster the rate of degradation. So that's also an issue. Every so many years, glass tanks have to be drained, shut down, disassembled, rebuilt. So one of the new things that has been invented at my group is something called lion glass. I can't take credit for the name. That goes to my dean. Thank you, Lee. Named after the Nittany lion, hence lion glass, because we all know the best glasses are named after animals. So this is our patent-pending family of glasses that is meant to be a replacement for traditional soda lime silicate glasses. So it's meant to directly address this issue of the carbon footprint of the glass industry by reducing the melting and forming temperatures by on the order of 350 degrees C, which is substantial savings in energy. And it's made from a chemistry that also, in parallel, eliminates the need for carbonate batch materials. So that part of the carbon emission is eliminated. The other part is greatly reduced. Traditionally, the problem with many low melting temperature glasses has been poor corrosion resistance, where they just kind of suck up the humidity from the environment and degrade pretty quickly. But this glass has corrosion resistance that is at least as good as soda limes, and also outstanding optical transparency. So this shows the log viscosity curve versus temperature for traditional soda lime silicate glass, and then for our new family of Lion glass, which is shifted down by about 300 to 400 degrees C. Optically, it is beautifully transparent here, and actually even more transparent than soda lime silicate. Now, if you take a window glass and you turn it on its side to sort of look through the width, what color is it? It's green, right? It's green because it's got trace amounts of iron impurities. You don't really notice it when you're looking through the 3 millimeter thickness, but if you turn it on its side, you can't even see through it because it's so green. With this new glass, it can actually take more iron contamination for the same amount of coloration, which is quite interesting. But if you want to put colors, you can also introduce all kinds of beautiful colors into Lion glass with different transition metal and rare earth dopants. And one of the interesting things about this is that it's actually a beautiful art glass. It reduces the temperature so much that it becomes a lot safer and easier for glass blowers to work with it. If you've ever seen glass blowing before, what you see is that, of course, it's very hot, right, at the end of the rod. The artist has to wear dark glasses to be able to protect their eyes. And of course, you know, they can get burned pretty badly if they get too close to it. With this glass, the temperatures are reduced so much it's no longer glowing at the temperatures where it's working, so they don't need to wear those dark glasses. It's a lot safer to work with, and because the radiative heat transport is greatly reduced, it's got a much longer working time, meaning it can stay out of the furnace for a lot longer before they have to put it back in to heat it back up again. So it's quite interesting there. The glasses are also looking great from the point of view of corrosion resistance with no visible damage there. So this is one of our exciting next developments in glass. But I'm hoping what I showed you today is that in this glass age, you know, glasses are critical to inform you with the display of information, to connect you through fiber optics, to heal you through pharmaceutical glass, even to clothe you. So actually, one of the coolest sets of research that's being done here is by MSc Professor Wulff, who has all this amazing research being done in fibers and like smart fabrics, and glasses are a part of that. So glasses can clothe you and house you and power you and enhance your reality. So with that, I will thank you and happy to take any questions.
Thank you so much, Dr. Mauro. That was a beautiful talk. And we now have time for some questions. Yeah.
Can you say anything about the qualities of Lion glass with respect to thermal shock, say, compared to soda lime glass?
Right, great question. So for thermal shock, there's multiple parameters. One of them would be worse for thermal shock. It does have a higher thermal expansion coefficient. Two of them would be better. It's got a lower Young's modulus and also a lower strain point. So if you think of thermal shock, you know, it relates to the strain that's being produced and then converted to stress. And so the integrand of that would be the thermal expansion coefficient, which is higher, but the limits of the integral go from you know, the strain point down to room temperature. So that part would be less. One of the interesting things, though, about Lion glass 2 is that I don't have the data yet, but we're working on it, that the mechanical properties seem to be favorable compared to soda lime silicate as well. And I'm hoping that this might also lead to basically reduced thicknesses of glass products. If we can achieve the same amount of mechanical performance at a lower thickness, then that light weighting can also mitigate thermal shock. It can also reduce energy consumption due to transportation. So we're going to be evaluating this. And great question. Thanks. Great. And you can ask me anything, by the way. It doesn't have to be about glass. If you want to know, like, what is it like to work in industry? What's it really like as a material science major? Anything you like. Uh-oh. It's Doctor Who.
Thank you, John, for this fascinating talk. I'm actually curious about discovery or about line glass. Is it a kind of iterative empirical process, or is there any machine learning or advanced modeling simulation that comes in?
It was kind of, thanks, JJ. It was kind of old school, honestly. It was more understanding some basic principles of glass structure and being informed by the literature to make some educated guesses about where we should be looking. Some of the other work that we've been done has been machine learning intensive. Actually, a lot of it has been. But this case, no, this was more old-fashioned approach.
Hi, thanks for the talk. Since you opened yourself up to all types of questions, especially regarding your industry work, I'm curious, now that you've left Corning, do you still get cuts, or did you ever get cuts from the patents of all the Gorilla Glass? And how much percentage do you get?
Okay, there's a sad truth I need to tell you about working in industry. So when you work in industry, part of the contract is that they own all the intellectual property rights to what you do. And so they are required to pay you something in exchange for that. But US companies really rarely, if ever, pay royalties on inventions. So the answer is, I got a $2 bill on a certificate glued to a sheet of paper.
Chris, did you?
I don't need the mic. So I like the idea of reducing processing temperature by a few hundred degrees. But if I want to cash in on that, do I need to build a different float line?
Right. So great question, Chris. So there's many different product spaces for soda lime silicate glasses. Some of them will be easier to enter compared to others. I consider float line to be like the most highly engineered platform for manufacturing soda lime. The simplest would be like art glass and glass blowing, and then maybe going to tubing and rods, and then to hollowware, and sort of working our way up to float. Because the cost that is involved with re-engineering the float process is substantially more. So I'd like to prove it and demonstrate that we can do this successfully on some other products and sort of work our way up to float. Now, if you change the question to be, in principle, should it work with the float process? Is it float compatible? I think the answer is yes, because the melting point of tin is so low, and it might actually be a chemically nicer, a shorter float line too, yeah. So I think in principle it should work, but it would certainly require engineering to bring it down to those lower temperatures.
Yeah, a lovely talk, John. I want to ask a 22nd century question, provided human beings are still here in 100 years. That's a good if right now. You're still using processes which, in fact, are not very different from what they were 3.5 millennia ago or more. That is, you're basically looking at raw materials that are carbonates or silica raw materials, and that's where the carbon footprint comes in. What about self-assembly with just atoms themselves? Because all you just need silicon, oxygen, sodium, some magnesium, and then other smaller quantities of other things. You don't need all this intermediate stuff that are causing you problems. Has anyone thought about whether that is scalable? You can obviously do it in extremely small quantities in the laboratory, but could any of that ever be scalable so that you can eliminate all of these intermediate steps, which we don't need?
Great question. So there's some work that's being done in that type of area at University of Wisconsin by Mark Ediger, working in the area of organic glasses, and he's looking at this like atom by atom construction of glasses and finding that he can build them to be a lot more stable, like equivalent to a much lower fictive temperature compared to traditional melt-quenched glasses. Is it something that is scalable? I think what you will see is that something like that would be great for making ultra-thin glasses or films, but not practical for making things with larger thicknesses. So the same way it's extremely difficult to make extremely thin sheets of glass using traditional methods. I think it would be difficult to make thicker pieces of glass with that method. But I think there's going to be a place for both, depending upon the requirements of that product space.
Yeah, John, thanks for that beautiful talk. So two related questions. One is your definition of glass is relaxed towards the supercooled liquid, but is it possible for it to nucleate a new crystal before it reaches that? And then the related question is there are radiation-induced solid-state amorphization, and you mentioned amorphous is maybe like a, different from glass, but what kind of relationship in terms of theory and stuff like that?
Sure, great. So for the amorphous question, so basically if you irradiate something, you could start with a crystal and basically it can become a distorted crystal. It could become an amorphous solid that would immediately crystallize if you were to heat it up again. Or you can make glasses that are irradiated enough that they actually enter a glassy state without first passing through the liquid. But the only way you could tell is if you were to heat it up in a DSC and see if you have a glass transition there. So if you observe a glass transition, then what you just measured was a glass. And if you don't, if you just observe crystallization peak immediately, then it probably wasn't. Now, you're right. Also, when you have a glass as non-equilibrium, it is continuously relaxing towards the supercooled liquid because it's connected continuously to the supercooled liquid. But that's only the metastable equilibrium. It could undergo, if it has a large enough perturbation, it could nucleate and grow crystals and get to an even lower free energy state. And so, yes, you're right that there can be different rates of kinetics where in some cases, nucleation and crystal growth would be faster. In other cases, relaxation toward the supercooled liquid could be faster. It can happen either way.
Maybe I'll ask just one. I have a lot of questions, but I have one that I want to ask you for now, and that is, you invented this kind of potentially revolutionary new material in a very short time, right? Lion glass, and I'm just wondering, like, what did you learn from your time in industry that you brought into academia, right? That you see as really important and valuable, and what could we all learn from you about that?
Oh, thanks. So I think one of the things that I learned from industry that's most relevant for this question would be understanding value propositions for things, because for anything that we're trying to do, there's kind of the existing way that people do it, right? There's the existing material, the existing product. In this case, the existing soda-lime silicate glass. People are comfortable with this. They've been using it for hundreds of years. And then when you come up with something new, that's change, that's scary. So there's resistance to change because of all the new engineering that's involved. So you have to demonstrate that there's value to that compared to what they're doing in order to incentivize people to make that switch. So your new material, it either needs to lower the cost so people can save money on it, or it needs to offer improved performance, or it needs to be government incentivized. And even for things like improving performance, is that performance improvement enough to justify the increase in cost that's associated with that? And so this is kind of an iterative process. You need to sort of get your customers' interest by with some sampling, get them to show them data, give them a couple pieces to play with. Once they're interested, you may think that you know what the value prop is, but you don't really until you have those in-depth discussions with the customers to understand where they're coming from. So you kind of work together with them to refine the value prop and to see if it makes sense to go forward. And in the end, both parties benefit. The customer benefits because they get something better than what they had before, and they're getting value from it, and they're giving a part of that value to you, and so you're making more money from that as well. So that's how it's supposed to work, at least.
Or for Gorilla Glass, I guess a $2 bill.
Well, that's the inventor, not the company. The company made more.
Okay, maybe this will be just the last question here.
So maybe a silly hypothetical question. I was wondering if you think if you hadn't grown up in Corning, would you still have gone on to do glass research today?
That's a great question. I don't know, because I've only lived this one life. If there were many parallel me's and parallel universes, I'm glad I have this universe. Other me's, I might have done something different. I might have been an English major. I hope I would have found my way to material science and engineering, because it really does have like the best of many worlds in there. And I joke about the English major thing, but that's important too, because it's not enough to just do your research. You have to be able to communicate that in writing and through presentations. And that's important for any major that you choose. But for material science and engineering, it's so many things that I love together. I love physics and chemistry and engineering aspects. I love doing something that's both fundamental and also can directly help people and even become ubiquitous. And when you think about like everything around us, made from materials. And material science, it's not something that a lot of like high schoolers would even know about, because it's not part of the standard curriculum. But I think, when people learn about this, they get really excited about it. And I think the more we can spread the word about all the exciting things happening in material science and engineering, the more people that will get coming into this field. And there are so many job opportunities afterwards too, whether it's in industry or academia or national labs. You can take this in so many different directions. So it's got a great way to sort of tailor the material science experience towards your own specific interests as well.
I do not want to stop you from talking right now, because let's thank Dr. Mauro again. That was absolutely fantastic. Thank you.